Thank you for the introduction, and welcome you back after lunch. Hopefully you can entertain everybody, keep you awake through this afternoon session here. And so what I'd like to talk about today is a discovery that we made at Dow recently. That was an evolution of previous projects, and what I'm going to do today is take you through that discovery portion of kind of how we got there and that evolution, and then talk about the kinetics and a little bit of the pathways and how this chemistry works. So let me just start where the discovery kind of based on. It started on our work in syngas. This was a while ago when we were the pre-shale gas era. We're trying to figure out how we're going to get carbon to make chemicals. And of course, the traditional feedstocks, naphtha, natural gas, could be to the traditional, but you can consider coal, biomass, plastic, all can be derived and converted into syngas. So it's a flexible feedstock as carbon becomes short. And what we discovered previously and had scaled up with some partners is this cobalt sulfide catalyst. The cobalt sulfide catalyst is a mixed alcohol catalyst. It takes syngas to light alcohol, so methanol, ethanol, propanol. That's important for Dow because we can basically start from a variety of carbon sources, but also we get to olefins when we dehydrate those alcohols. And so we scaled this up. We had a number of partners. National Energy Lab, Northwestern, Georgia Tech, Chris Jones, and actually Bob Davis was also a partner back there, and had the catalyst scale up, demonstrated long lifetimes, high alcohol selectivities, and partnered with NREL on this material to basically demonstrate it in a pilot reactor at the National Energy Lab. And with that pilot, they were actually feeding a biomass-derived syngas for the catalyst, and it demonstrated lifetime productivity. And in that work, we just did a technological analysis, did process design, and showed that you could actually produce ethanol at a selling price back in, this is 2012, so this is a while ago, for a little over $2 a gallon for break-even economics. And there was quite a bit of work that went into this evolution of the cobalt sulfide catalyst, and that evolution included high throughput analysis, high throughput testing, catalyst synthesis, as well as kinetic analysis. And this was just a pictorial of kind of the pathways that were present on the moly sulfide catalyst, and a proposed pathway to agree with our kinetics is it basically was a hydrogenation of CO to form a CO intermediate that had lots of hydrogen activation reactions to basically activate that CO, produce an alkyl with CO insertion and another hydrogenation to grow carbon chains, hydrogenation to make the alcohols. What you see in this mechanism, these pathways, is a number of hydrogen steps that convert CO, produce the alcohols, and this was what we determined was important for the moly sulfide chemistry. And you also see here a number of other molecular intermediates that we're forming, things that we get to esters, you get to the alcohols, you get the hydrocarbons, depending on the intermediates on the surface. So because of this complex chemistry, carbon growth, hydrogenation, CO insertion for further carbon growth, we basically thought, at the end of that campaign, after we had scaled it up, what else could we do with our sulfide catalysts that we had in these laboratories? And so, the chemistry we started thinking about was, we started with syngas. Instead of doing the direct syngas to products reaction to cobalt sulfide is what else could we add to syngas to do carbonylation chemistry? Do chain growth, type of selective chain growth, to see if we can produce molecules of interest. So, a variety of alcohols, olefins, esters, acids, basically things with, carbon growth in a selective process using a high throughput reactor that we had used to do the cobalt sulfide work. This high throughput reactor is a 48 parallel channel reactor with a detailed analytical that included, calibrated alcohols, esters, ethers, aldehydes, ketones, hydrocarbons. So a number of products we can quickly then screen these different chemistries and just look for effectiveness across a variety of materials. The materials came from the libraries we produced as we were working on the cobalt molysulfide catalyst. We had these libraries on hand. Straight molysulfides, a whole family of molysulfides with different level motors, different levels of alkali addition to those, a family of tungsten materials, some chrome materials, and a selection of other sulfides, monometallic sulfides with and without alkali as well. So we had these in libraries, so we took, we crossed these campaigns of these libraries of sulfides we had against the different chemistries and went for evolutionary studies, seeing what could we find in these materials and these chemistries that wasn't known. And lo and behold, we came across methoxycarbonylation that worked extremely well. Essentially, ethylene, CO, methanol, so no hydrogen, so it's a straight methoxycarbonylation reaction to form methyl propionate. And it actually occurs over a variety of sulfides, with cobalt sulfide being the most selective and productive of the bunch, but it does occur over the other sulfides as well. And this chemistry the world hadn't described before. I mean, methoxycarbonylation is commercially practiced over a palladium homogeneous catalyst, but never a description of sulfides being able to do this chemistry known at all, or even mentioned in any literature or any other patents. So it really was a new to the world discovery that you can do this with extremely high selectivity at good conversions. The other thing that's interesting is that it's atom efficient. I mean, yes, you take 3 molecules and get 1 out. With, no byproducts, no water formation, no CO2. Right? It's a nice clean reaction, which makes it relevant. Just a flavor of the other products that are made. If you look at the other things that are made of this high selectivity, this is 90 plus, to 98% selective. This was the one with the higher conversion. Showing that you also have a route to methyl acetate, a little bit of hydrocarbons, a little bit of acid, small amounts of aldehydes, a little bit of CO2. So really not much else. Pretty clean chemistry with a little bit of methyl acetate. But as you continue to optimize materials, conditions, you can drive this to extremely high selectivity and specificity. This is all of the initial discovery, all of the high throughput reactor actually that this discovery came out of. And this is in the early initial results. And it's also stable. Of course, with catalysis, it's great. It does chemistry for a short period, but we also show that at a variety of space velocities, you also can demonstrate the stability of the catalyst, showing the selectivity stability. This is still over a couple of days, but selective and stable. And this is the conversion of CO, ethylene, and methanol. Again, all showing fairly stable operation over a variety of space velocities and conversions over a couple of days on stream. To kind of do a quick demonstration, I will just say quickly, but yeah. So how does this work? When we looked back at the mechanism of molysulfide, remember I talked about how it was a hydrogenation catalyst. It actually does hydrogen splitting well and does hydrogenation fairly well. The cobalt sulfide, we believe, shuts off this hydrogenation catalyst. So now we had also lack of hydrogen, but it also doesn't do hydrogenation. And so that basically closes down a number of these mechanistic pathways that molysulfide is using to grow carbon to make these mixed alcohol products that we're working on the cobalt molysulfide catalyst. So that we really have to go back and think more. Since it doesn't do hydrogenation, how are we activating CO and doing carbonylation chemistry? And if we look at the literature of the homogeneous catalysis, because this is where it is practiced and works, palladium, methoxycarbonylation mechanism here. What I highlight here is this is a hydride mechanism. So what I highlight is in red is methanol forming this hydride. We'll keep these as empty sites here, but this is a hydride that forms on palladium. You do a alkyl insertion to form a alkyl intermediate, and goes to CO insertion to form a acyl intermediate that then, through methanolysis, basically absorbs the ester product. And that's the route for palladium methoxycarbonylation that has been well established now in the literature. And that's palladium, doesn't exactly match cobalt, as we said, whatever literature is out there. In a cobalt homogeneous catalyst for cobalt carbonyl, it does hydroformylation. Hydroformylation is similar in chemistry, except you lead an aldehyde. But it also has a similar mechanism where you form a hydride, and that hydride then does the same thing. It reacts with the olefin to form a alkyl intermediate. The alkyl intermediate goes through a CO insertion, form that acyl intermediate. In this case, it's hydroformylation, there's also hydrogen present. That hydrogen then eliminates the form of the aldehyde. So, again, another clue that this hydride mechanism might be at play on our cobalt sulfide catalyst. And again, you can see how we kind of, this is a simple path, but you can see how we show that the methanol activates to form that hydride, ethylene insertion into the hydride there, CO insertion from the acyl intermediate, and then a condensation with methanol to eliminate the product. But what about the materials? The materials, cobalt sulfide structures are dynamic. There's a number of stable structures that can form. The cobalt sulfide structures range in stoichiometries and oxidation states. And this is a plot of formation energies of a variety of these cobalt sulfide structures, looking for what bulk sulfide would be stable under a variety of conditions. And this initial work points to a stable phase being a CO9S8 phase, being kind of the well of stability. But all these phases are known under different synthetic conditions. So just a clue of what phase may be stable. And when we bring in DFT and do some modeling to try to look at how these intermediates can absorb and react, what we found, and actually with the literature, there's some literature on cobalt sulfides that's based on, this is literature reference here, which is based on water splitting. So water splitting is, as maybe you know, it's been popular in the past. And cobalt sulfide is one of the catalysts that works for water splitting. So taking some inspiration from water splitting, we'll also describe a variety of phases and CO9S8 being relevant in there also. What is relevant in that literature is the formation of a sulfide. The structure of these sulfides are flexible. So you can take the sulfur in and out of these structures. And what you see is when you form this sulfur vacancy, it forms a hollow site where you can do reactions and bind things. And what we calculated by my colleague what she showed is looking at the binding energies of a variety of the molecules of interest, CO, ethylene, methanol, and also looking at methanol splitting and the energetics of that on a variety of sulfide phases, as well as on the blue bar is on a clean surface, and then the yellow bar is when there's a vacancy, and showing the different energetics of the absorption. Most of these will absorb CO and ethylene reasonably well as methanol. But where the differentiation comes in is this splitting of methanol. You try to activate the methanol, you'll see on the cobalt sulfide structure, essentially the clean surface, she couldn't even get to the half, it would just absorb, so she didn't put a bar there at all. And it's also uphill heating for vacancy, so pretty substantially uphill. CO3S4, similar story in that to split it, the structure on a clean surface was extremely uphill here, and in a vacancy, it would bind, but it's still endothermic chemistry. However, on the CO9S8, with this vacancy, as described here, you actually could get a reaction that was exothermic with a significant binding of the intermediate, which is basically the formation of that hydride. So all, again, consistent with a CO9S8 being the structure of interest for this chemistry and an effective structure of that. You have the basic form of sulfur vacancy. As you can see, without that vacancy, it's extremely uphill. So, again, this is a representation of the surface. As we know, complex sulfide or oxide structures in DFT is challenging, but again, a reasonable suggestion about how this could occur in binding and activating that methanol. If we look at the free energy diagram, I don't know barriers, but we can at least look at the free energy diagram, and this describes the binding of the different molecules that I showed on the previous slide, but also it shows important reactions. Important reactions being the C2 hydride reaction. So this is the reaction of the alkyl with this hydride to form the bound alkyl on cobalt. CO insertion reaction up here, reaction to get that CO to insert into that alkyl bond, and then finally the methanolysis, which then forms and absorbs the ester. again, this is some indications from energetics of plausible pathway, but it really doesn't get to what's a rate determining step, what controls this chemistry. And to address that, we collected some kinetic data. The kinetic data was collected over a range of space velocities, temperatures, pressures, compositions, all on actually the same materials, running over 300 hours on stream. So again, it speaks to the stability of the system. Just a couple of quick plots of logarithmic rates versus pressures is when your activation energies look all reasonable. But just to show you the fit, but ultimately we started with the power law. Keep it simple, right? And let's see how does this behave. Just give some indications of the chemistry. We look at the power law fit, and what do we get? We get a CO that's really zero order. So zero order in CO under these conditions. Half order in ethylene, and higher order even in methanol. Okay, CO order of zero maybe makes sense. CO covered surface. Half order in ethylene doesn't really make sense. We're not splitting ethylene. We're not doing it into a bimolecular reaction. So half order really don't make a lot of sense for power law fit, and I'll have the methanol. So we decided we would come up with some more plausible mechanistic thoughts and feel a more complicated model. And the ultimate indication of the activation is around 80 kilojoules per mole. And of course, the power law does give a pretty reasonable fit to parity spot. So yeah, not an unreasonable fit, but it doesn't give us a real insight into the chemistry. If you look at the Lagrange version of the model to try to get us a little more insight into what's covering surfaces and what's active, you basically get, it's three molecules to come together to form the ester here, right? So they're the numerator. They look at what's covering the catalyst, and as we try to fit this, terms drop off. Like this is the ethylene bond, and that basically went to zero. And a good indication of this actually fits the model with this hydride mechanism where ethylene is the rate determining step. So the activation of ethylene on that hydride is what we show to be rate determining step, and it just fit this model well. So consistent with that mechanism. And you also can see then a little closer what this next to the meter looks like. The ethylene is bound to the cobalt, so that's where the hydride was. Ethylene then reacted there to form this alkyl intermediate, and CO actually binds this hollow site. This is where the vacancy was. You take that sulfur out, and this CO combines. You actually three cobalts in that vacancy that happens there. Then of course, when the CO insertion happens, there are that cobalt. So kind of what it looks like. And so, yeah, so I hope in my time today, I can talk a little about how we got to this discovery, a little bit about how we have some ideas of how it might work, and the relevancy of sulfur vacancies to actually make this chemistry work. And with that, I will also give you a preamble for a talk that's going to come in on Wednesday. So my colleague, Beata is going to be talking about more about the sulfide chemistry. She's going to talk more on the structure side, a little more information about the cobalt sulfide structures that exist in this chemistry, but also talk about another carbonylation chemistry from aluminum carbonyl, some work to do with Justin Notestein for propionic acids. So her keynote will be on Wednesday for those that want some more information. So thank you very much for your time, and entertain any questions.
So, how appropriate is the substrate?
Yeah, it works on many of the alkyls. It opens it all carbonyl.
Selectivity.
It's also good.
What's the ratio chemistry?
Split. It actually it doesn't form highly selective to either. It's kind of balanced in the ion, so it's not clean to one or the other.
Okay, I think it's time for us to transition to our next talk. Let's thank our speaker again.